Hello everyone, welcome to the preview session of Lesson 33. In the past 4 weeks, we've learned about the congruent triangles and similar triangles. In this week and next one, we're going to explore more in triangles. To be more specific, we're going to talk about special lines in them. But before that, let's be familiar with a very important concept, the distance. If you have a point R and a line T, to find the distance from the point to the line, you just need to draw a perpendicular line passing through the given point and intersecting with the line at point S. Then the length of segment RS is exactly the distance from the point to the line. So remember, distance always means perpendicular. Okay, so if you are given a diagram like this, the angle ABC is bisected by the red ray BP. P, we say the point P is on the angle bisector of angle ABC. And let's prove point P is equidistant to the both sides of the angle ABC. Equidistant means Px, the distance from P to the arm AB, should be equal to the other distance, that is Py. How can we prove that? If you do some labeling on the figure, the angle bisector tells us something about equal angles. And then you notice equal angles because they are both 90 degrees. And you have a common side right over here. So angle, side. We can prove that triangle BPX is congruent to triangle BPY. And in the brackets, let's have our reason for this argument. That should be AAS. Okay, so after prove the congruent triangles, you can have their corresponding sides equal. That's a very important property of congruent triangles. So Px equals Py. That's how we prove the angle bisector equidistance theorem. Sometimes you may come across the theorem without this word, but I prefer to keep this one in this lesson. Okay, and the next important idea is perpendicular bisector. This time you are given a line segment like JK and you know the midpoint of it, that's M. So passing through the point M, you draw a line that is perpendicular to the given segment. Perpendicular, and the line is the perpendicular bisector of our segment JK. So why are we interested in a line like this? That can be something related to equidistance. Again, we take a point A on the line L, and then we try to find the distance, this time the distance between 2 points, AB or AC. It looks like that they are equal due to congruent triangles. If you can still remember what we did to prove that equidistant of angle bisector in the previous page, you can try to prove triangle ABX and the adjacent one, triangle ACX. Let's prove they are congruent. You have perpendicular bisector, so x is the midpoint, so bx equals cx, and the common side. Don't forget that. The common side will always be helpful. And perpendicular, so this word means we have 90 degrees, 90 degrees. Side, angle, sides. Of course, they are congruent triangles. In the brackets, let's have SA as our reason. Okay, so AB, of course, will be equal to AC. So the theorem is about perpendicular bisector. If we take a random point on the perpendicular bisector, the congruent triangles will always be true. So AB will always be equal to AC. So all the points on the perpendicular bisector of a line segment are equidistant to the both endpoints of the given segment. We can prove that with congruent triangles. Okay, that's all for our previous session. See you in the classroom.